Professor David Sokoloff, sir, who is our keynote addressee. Professor David Sokoloff, sir, is an emeritus professor at University of Oregon, USA. He earned his BA at Queens College of City University of New York and his PhD in atomic and molecular physics at the MIT, USA. For over 3 decades, he has studied students' conceptual understandings and developed active learning approaches with NSF and FIPSE support. These include interactive lecture demonstrations and 4 modules of real-time physics, active learning laboratories, both published by Wheeler and co-authored by Priscilla Lodge and Ronald Thornton. His work has been published in the American Journal of Physics, the European Journal of Physics, and the Physics Teacher. He has conducted numerous international and national workshops to disseminate these active learning approaches to secondary and university faculty. Since 2004, he has been the part of United Nations UNESCO Active Learning in Optics and Photonics ALOP team, presenting workshops. Till date, he has presented 37 workshops in developing countries in Africa, Asia, Eurasia, and Latin America. He is a contributor to and editor of the ALOP training manual, which is a very good manual for right from school teachers to college teachers in optics and photonics. The ALOP team was awarded, which Dr. Professor Sokoloff, sir, is the part of this ALOP team, was awarded the 2011 SPIE Educator Award. He was awarded American Physical Society 2010 Excellence in Physics Education Award with Priscilla Lodge and Ronald Thornton, and the American Association of Physics Teachers AAPT 2007 Robert Millikan Medal. In 2020, Hans Christian Ørsted Medal. He has been Fulbright Specialist in Argentina 2011 and Japan 2018. He is currently member of International Union on Pure and Applied Physics, a commission of 14, International Commission on Physics Education. He served as an American Association of Physics Teachers President in 2011, again, which is one of the prestigious positions in USA. With these words, I request Professor Sokoloff, sir, to deliver his keynote address on active learning of introductory optics, strategies for US and the developing world. Professor Sokoloff, sir, please.
Thank you very much for your introduction, your gracious introduction, and thank you for your invitation. And this is my 4th visit to India, but this time, unfortunately, it is virtual, but I hope to come back live sometime. Can you see my, do you see my screen?
Yes, sir.
You see my
yes,
PowerPoint?
sir, yes.
Okay, very good. All right, so I will start. Oh, by the way, to all the participants, you may know tomorrow is election day in the US, and we elect hopefully a new president, a different one. But okay. I want to mention that I have 2 colleagues who I've worked with for many years, for over 34 years, Ronald Thornton and Priscilla Laws, and together, as was mentioned, we were awarded the American Physical Society Excellence in Physics Education Award in 2010. And also, I should say that in the US, we are very lucky to have financial support for development of educational strategies, the National Science Foundation, and the US Department of Education. Here's an outline of my talk today. I want to talk about the problem and the need for active learning, the characteristics of active learning, optics activities in real-time physics active learning labs, optics examples of interactive lecture demonstrations, research on the effectiveness of these materials, and UNESCO's ALOP, or Active Learning in Optics and Photonics teacher training program. And then finally, a brief look at interactive lecture demonstrations online, which is especially appropriate for the situation that we're in right now with the pandemic. So to start with, what is the problem? Well, students come into an introductory physics course at the high school or college level with definite views about physics because they have done a lot of physics experiments in their lives. They ride bikes, they walk, they do lots of things that involve physics, and they have ideas. Physics education research shows that, number one, many of those ideas are wrong. They don't describe the physics correctly. And furthermore, that the vast majority of students can go through an entire introductory physics course and not change their incorrect views. So come out of the course with very little understanding of physics concepts. And this research has been done in many forms, by interviewing students, by giving them open-ended questions, short answer questions, well-designed multiple choice questions, and the same conclusion is reached, namely that it is traditional methods of instruction that are the problem, regardless of the skill of the instructor. So I don't know if you know Bart Simpson, but basically he would say, I do not learn concepts in physics class. Or perhaps you know Sheldon from Big Bang Theory. How can they possibly not learn from my perfectly logical, sublimely entertaining lectures? So the proposed solution is active learning environments. And just to be very clear, these are not meant to replace, but are meant to complement the more quantitative work that we do in a physics class. Because it's important to deal with physics quantitatively, how to solve problems, but it's also important that they come out of a physics course understanding the basic principles. So what do I mean by active learning? Well, here's a table that compares passive or traditional learning to active learning. In passive learning, in traditional instruction, the instructor is the authority. All information flows from the instructor. But in an active learning environment, the physical world is the instructor. Because in real life, that is true. It is the physical world from which we learn. So the instructor's role is as a guide for the students. They learn from the physical world. In a passive learning environment, students' naive beliefs that they bring into the course are never challenged. But in an active learning environment, we use a learning cycle, prediction, observation, comparison. This challenges the students' beliefs. In a traditional learning environment or passive learning environment, collaboration with peers is often discouraged. But in an active learning environment, collaboration and shared learning with peers is encouraged because students can learn from each other very well if they have the information from observations to base their discussions on. In passive learning, experimental results are often presented as facts. But in our active learning environments, the results from real experiments are observed in understandable ways, often in real time, with computer-based tools. And then finally, in passive learning environments, experimental results or laboratory work is used to confirm what was already learned in lecture. But in active learning environments, the laboratory is a place where students learn the basic concepts of physics. Excuse me. Now, sometimes people are confused. They say to me, active learning and hands-on are the same thing, but they're not. Active learning requires much, much more than hands-on. And let me give you some examples. You can do the most fun, exciting, and compelling lab experiment or lecture demonstration, and that is hands-on. But it is not active learning if the students are not engaged by making predictions and having discussions. And furthermore, or the counterexample, you may be familiar with Eric Mazur's peer instruction. This is a strategy that usually involves no hands-on at all, and yet is a very active learning strategy. So a better term would be both hands-on and minds-on. That would be more accurate. And a large part of active learning is getting students engaged in the learning process. So I want to give you some examples of active learning curricula that are designed for the introductory physics course. And the two I'm going to talk about briefly are real-time physics, which are active learning laboratories, and interactive lecture demonstrations. So let me start with real-time physics. Real-time physics is a series of lab modules that use computer-based to aid students in doing experiments that help them to develop important physics concepts while acquiring vital laboratory skills. Or let me rephrase that. Students doing real-time physics do real experiments in a laboratory, but they're aided by the use of microcomputer-based tools. And the labs are set up in such a way that it challenges them, are challenged while they are also doing lab work and learning laboratory skills. So what are the goals? To help students acquire an understanding of physics concepts, to provide students with direct experience of the physical world by using computer-based tools and real-time data collection, to enhance traditional lab skills, and those are the basic goals. There are 4 modules of real-time physics. They have been published by John Wiley and Sons: mechanics, heat and thermodynamics, electricity and magnetism, and light and optics. And I'm going to give you some examples here from light and optics. Now, by the way, accomplishments of the activity-based physics group that I'm a part of has been the development of a number of uses of technology to explore the physical world. So, for example, computer-assisted data acquisition tools, video analysis and capture. So here are 2 examples from real-time physics module 4, light and optics, that use technology to help students learn basic optics. These labs are designed for students in an introductory physics course. So let me first show you an example from a lab called polarized light. And here you see the equipment. There is something called a rotary motion probe, which is right here. And it is a device that measures angle very precisely. And mounted on this rotary motion probe is a piece of Polaroid, a piece of linear polarizing filter. And behind the probe, behind the polarizer is a light probe. And in front of the polarizer is a flashlight, which is the light source. And the light source has another piece of linear polarizer in front of it. So the light coming from the flashlight is linearly polarized. And this piece of Polaroid on the rotary motion probe can be the analyzer for the light. So let's see what happens. If we turn on the light and rotate this piece of Polaroid, we get a graph that looks like this. And those of you who are physicists recognize that in Malice's law. But of course, students don't know anything about Malice's law. Students look at that curve and they say, oh, it's a sine curve, or it's a cosine curve. So And of course, it represents the fact that as you rotate the analyzer, sometimes the axes are crossed and sometimes they're not crossed. How would we know what the actual function is here? Well, we can do some modeling. We can put in an equation, which is the orange line here. This is a calculation using an equation. These are the real data. And this equation, you can see here, it's a little bit hard to see, is a cosine squared of the angle. And so by doing an analysis like this, we can see that the actual dependence of the light intensity is a cosine squared of the angle, which of course, as we know, if we know Malus's law, that is what Malus's law is. It's a cosine squared dependence. Okay, anyway, that's one use of technology. Here's another example of a use of technology. In the next lab, waves of light. And this time, it's the same rotary motion sensor, but it is mounted, the wheel is mounted so that it's rolling along the table, along this meter stick. The light probe is, again, attached to the probe. And over here, we have a laser and a double slit. So the light probe is looking at the light pattern from the double slit with red light from the laser coming through it. And if you scan the light probe across the table like that, you get a graph that looks like this. And that graph, as many of you recognize, is the intensity pattern of a two-slit interference. Here are the interference fringes. And you might also notice that, in fact, they are modulated. And how are they modulated? Well, if we look instead at a single slit of the same width, we get a single slit interference pattern that looks like that using the same method. And if we superimpose them on top of each other, we see that the two-slit interference pattern is modulated by the single slit. So we can learn an awful lot, in this case, by using some very relatively simple but actually fairly sophisticated technology. Okay, now here's the thing. These tools are very nice. They're very nifty. But as we'll see later on in my talk, you don't need fancy tools to learn about optics concepts. I'm showing you these as an example of how technology can be used. But it's the careful design of the tools that allows us to change the pedagogy, because these labs are designed very carefully to ask students to make predictions and to make their observations and to make the learning much more active. Okay, my second example in this talk is to answer the question, can an active learning environment be created in a large lecture? Because many of us teach very large lectures. I'm sure many of you do. I often teach lectures with 200 students in them. And lecturing is a very passive activity. So maybe you experience something like this. Professor Sokoloff, may I be excused? My brain is full. Students can only absorb so much information, and physics is, of course, a discipline where it's not even good enough to absorb the information. You have to absorb and interpret the information. So very little learning of physics concepts takes place in a lecture. And that's very well documented by physics education research. So can an active learning environment be created in a large or small lecture? Well, my answer is yes, through the use of interactive lecture demonstrations. So I want to show you what I mean by interactive lecture demonstrations. So I'll give you an example and this is an example on image formation in optics. And here's the way it'll work. I'll show you a demonstration and ask you to make a prediction. And I'm actually going to ask you to make a prediction. So we'll get to that in a second. By the way, when we are teaching students, we make sure that students know that predictions are not graded. A prediction can't be right or wrong, because the only way we know that a prediction describes the physics correctly or incorrectly is by doing an experiment to observe. So predictions are not graded. And why is it important to tell students that you don't grade predictions? Because if you tell students that you're going to grade their predictions, they will try to predict what they think you want them to predict, not what they think themselves. So it's very, very important to make sure that you tell them that their predictions are not going to be graded. Now, it's possible that you might award them some credit if for participating and for turning in their predictions. Now, if we were together in a lecture room, I would ask you to discuss your predictions with your nearest neighbors and see if you can agree with each other or reach a consensus. Now, we're not together, and I don't want to use chat rooms in my talk, so therefore I'm going to dispense with this step. But in real life, if you were teaching in a lecture, you would ask students to have small group discussions. And then finally, I will do the demonstration and display the results to you, and I would ask you to discuss what you observed with the whole class if we were actually all together. Now, actually, I'm not going to do a demonstration for you, but I'm going to show you photos of the demonstration. All right? So here we go. If we were actually doing this, I would give you a prediction sheet that looks like this, and I'd ask you to make a prediction on it. So in demonstration number 1, it says there's an object, which is the arrow. You can see it's outside the focal point. There's a lens. Let's make believe that it's a thin lens. And it asks you to draw a ray diagram to show how the image is formed. And then it asks you, is the image real or virtual? So I'm going to give you 3 minutes to draw a ray diagram. Would you please do that? Individually draw a ray diagram, okay? So I'm going to get a glass of water while you do that. 3 minutes from now, I will come back. That's 1 minute. Can you still hear me okay?
Yes, sir.
Good.
Yes, sir.
Okay, good. Okay, let's say 1 minute more. What was that? Okay, 30 seconds and then we'll come back. Everybody should be making their prediction, should be drawing a ray diagram. $15 seconds. Okay, now normally, if we were all together, I would ask for some volunteers to describe the ray diagram that they drew and to talk about whether the image is real or virtual, but we can't really do that very easily here. There's so many people who are participating do that, but I just want you to know that that would be the next step. And I will summarize the steps in just a little while. So what I'm going to do is let me show you the apparatus. So here is a lens. It's actually a thick lens, but you can see the lens here. And over here is the object. And you can't see it very well. It's a little bit blurred, but there's a light bulb at the top of the object, and there's a light bulb at the bottom of the object. So that's my experiment. That's my apparatus. And what happens if I turn the two light bulbs on? This is what I get. And again, I could demonstrate to you I could block one of the light bulbs or block the other light bulb so you can see that the light from the top light bulb is going like this, and the light from the bottom light bulb is going like that. And I could convince you that this is the image, and I would ask for some volunteers to tell me whether the image is real or virtual. But again, do this live, so I will just say the image is real because the light from this light bulb converges to that point, and the light from this light bulb converges to that point. And so if I put a screen here, that light would be focused on the screen, and that's the definition of a real image. Okay, so now what we're going to do is we're going to go to demonstration number 2. And I'm going to give you 1 minute to think about it and to predict what would happen to the image if I blocked the top half of the lens with a card. So I put a card in front of the top half of the image. The top half of the lens. What will happen to the image? So please, you have 1 minute to make your prediction. Actually, write it down if you have a piece of paper where you can write it down. "30 seconds. Okay, again, I would ask for volunteers from the class to tell us what they predicted. And I will just mention to you, in case you have never tried this with your students, that the most common predictions from students are, number 1, that half the image would go away, so we'd only see half of the image. Or number 2, that the whole image would go away. There would be no image at all. I can explain in a little while why students say that. But first, let's go and see what this looks like. So now I'm going to show you the demonstration. And there you see I am holding a card covering the top half of the lens. And you can see that light from the top bulb is still going to here, and light from the bottom bulb is still going to here. So the image is still in the same place. It's still inverted. It's still real, but it's dimmer because only half as much light. Now, if I were doing these as interactive lecture demonstrations, I would not be telling you that. I would be having volunteers of the students describing what's going on here. That's very important. The students are the ones who have to be talking, not me. By the way, demonstration number 3, which we're not going to do, asks what happens if you block half of the object rather than half of the lens. And here's what happens if you block half of the object. If I block the top light bulb, then no light from the top light bulb or from the top half of the arrow can go through the lens. It doesn't hit the lens, and therefore half of the image will disappear. Okay, let me summarize for you the steps of interactive lecture demonstrations. There are 8 steps. Describe the demonstration and do it for the class without the results displayed. Ask the students to record their individual predictions on the prediction sheet. Have the class engage in small group discussions. Elicit common student predictions from the class. Ask each student to record the final prediction on the prediction sheet, which will be collected. Carry out the demonstration and display the results. Ask a few students to describe the results and discuss them in the context of the demonstration. And students can fill out a results sheet, which looks the same as the prediction sheet, but which they can take home with them. And finally, if appropriate, discuss analogous physical situations with different surface features. And in this case, I would ask students if they can think of an application of this, that if you block half the lens, you still see the whole image. And there are 2 very good examples which students often come up with. One is in a camera, when you close down the aperture, you're blocking a good portion of the lens, and yet you still see an image of the whole object on the film or on the CCD element in a digital camera. Or the human eye. When the iris in your eye closes down, when you go from a dark space to a bright space, you still see the entire image. Okay, so those are the 8 steps, and those 8 steps are done for each of the short demonstrations that make up a sequence of interactive lecture demonstrations. Now, at the end of the talk, I'm going to show you a set of home-adapted interactive lecture demonstrations that students can do at home, but working by themselves, which I developed because of the pandemic, because many, many students around the world are learning from home and not attending classes. So we'll get to that in a little while. One question that you must ask if you're developing new materials is, do students learn better? And in this case, do students learn better from the image formation interactive lecture demonstrations? So we've developed a number of multiple choice tests. One of them is the light and optics conceptual evaluation. And here's one set of questions on that evaluation. There's an object, there's a lens, and there's a real image formed on a screen. And the questions ask, what will happen if you make certain changes? So you block half the lens, you block half the object, you remove the lens, you move the object further away from the lens, and so on. Those are the questions. And this is a multiple choice test, so the students are given choices that correspond to all of the answers that they might come up with. So it's not this kind of test. It's not a test where students are asked a fact. This is a joke. Bonus question. What's the name of that thing that hangs down in the back of our throats? Asking the name of something is not asking a concept. It's asking a name. Students often can remember names, but that doesn't mean that they actually understand anything. So it's not that kind of a test. So here are some results from my university, introductory physics students. After traditional instruction, which means all the lectures that I'm going to do on image formation, all of the problems in the textbook that they've done, reading the textbook, there's only a 20% gain from the pretest. But after, here's Bart Simpson again, but after doing 1 hour lecture of interactive lecture demonstrations, there's an 80% gain. So the students learn quite a bit from doing this type of demonstration, interactive lecture demonstrations. There's also a question that's like a ray diagram. You see that there are 4 rays that are drawn, 2 from the bottom of the arrow, the dashed ones, and 2 from the top of the arrow. And the students are asked, continue these rays to show how this image is formed. After traditional instruction, only a third of the students will do that correctly. And after 1 lecture's worth of ILDs, more than 3/4 will do it correctly. And by the way, notice that to answer this question, all you have to know is that for a perfect lens, every ray that leaves a point on the top of the arrow and hits the lens has to be focused to the same point on the image, and every ray that leaves the bottom of the arrow has to be focused to the same point, namely the bottom of the arrow on the image. And so it doesn't have to be special rays. These are not special rays in any way. They don't go through the focal point. They don't go through the center of the lens. By the way, why do we use miniature light bulbs instead of using a ray box for these demonstrations? And the answer is that the research that's been done shows that students don't understand that an infinite number of rays emanate from each point on an object. And that, as I already said, for a perfect lens, all rays from a single point on the object that are incident on the lens will be focused to the same point on the image. Instead, they are used to seeing just 2 rays. And so you can imagine, by the way, if they're thinking in terms of 2 rays or 3 rays, that when you block half the lens, you're going to block 1 or 2 of those rays. And that's why they come up with answers like there will only be half an image, or there will be no image, because some of the rays are gone. So that's why in the demonstrations that we do, we have them see all the light from point sources, which are light bulbs, rather than using individual rays. Why do the students learn better from these active learning curricula? Making predictions requires students to consider the beliefs that they have before they make observations of the physical world. So the real-time physics lab, the interactive lecture demonstrations build on the knowledge that they bring into the course. With interactive lecture demonstrations, the process of making predictions, defending them in a small group, and then writing down the prediction on a sheet that's going to be collected engages students. They want to know what will happen in the demonstration. So we've caught their attention. And there's a disequilibrium when they see that the result is different than what they predicted. And this is the opportunity for them to learn and to construct their knowledge from their observations of the physical world So they're building they're also building their confidence as scientists, because that's what scientists do. They base their knowledge on observations of the physical world. And by the way, there's been some research now, some of it from the Physics Education Research Group at Harvard University of Eric Mazur, that shows that if you do a lecture demonstration with your students and you don't ask your students to make a prediction before the demonstration, the majority of your students will not be able to describe the outcome of the demonstration after lecture. In other words, they won't, even though they sat there and watched the demonstration, they won't actually be able to tell you correctly what happened in the demonstration unless you engage them, unless you catch their attention before doing the demonstration. Okay, how do we choose ILD experiments? They're simple single concept experiments that build on each other. Students must trust the apparatus, so we must do some very simple things first. And many of the lecture demonstrations that we do, I don't know if most classes in India you do demonstrations, but in the US, in large lectures, we love to do demonstrations, but they're too complex for students to learn from them. How do we use ILDs? To introduce concepts, to clarify concepts, or sometimes in conjunction with lab activities. Now, there's a book called Interactive Lecture Demonstrations that has all the information on 28 sets of interactive lecture demonstrations. You can download this book electronically. It's a PDF, and you've been given the link, which is listed here in the chat in this talk. So you can go to the Teams chat that's part of this talk and copy down that link. And then you can download the entire book for free. There are 4 optics ILD sequences: reflection and refraction of light, image formation with lenses, which is the one that I showed you, mirrors, and polarized light. And I'm going to show you the polarized light one in just a few minutes. Okay, so now you have an idea, I hope, of what active learning is. And I want to talk about a program that has tried over the last 16 years to share active learning strategies around the world, and especially in developing countries. And the program is called Active Learning in Optics and Photonics, ALOP. This is the poster for an ALOP that was done in Sao Paulo, Brazil in 2006. I like this poster very much. ALOP is a project of UNESCO with support from many, many other agencies, especially from SPIE, which is the International Organization for Optics and Photonics, the International Engineering Organization for Optics and Photonics. The main creators of ALOP are Mila Alarcon, who was the first director of ALOP and who is now retired from UNESCO in Paris, and Alex Mazzolini from Swinburne University in Australia. And the current director of ALOP is Joe Niemela from ICTP. Some of you may know him. Here's a picture of one of the first ALOPs, a photo of the participants in the second ALOP that was held in Monastir, Tunisia in 2005. And you may recognize now Suad, who spoke to you earlier. This is Suad 16 years ago. As mentioned before, there have been 37 ALOPs since 2004, 15 in Africa, 10 in Asia, 9 in Latin America, and 3 in Eastern Europe or Eurasia, And by the way, of the ones in Asia, 3 of them have been in India. Delhi in 2006, that was one of the first ones. Mumbai in 2018. And I think, as mentioned before, in Pune, just this past December 2019. So what is ALOP? It's a teacher updating in optics and photonics. It's an introduction of innovative active learning approaches to faculty in developing countries. It's hands-on, minds-on learning. It uses simple, inexpensive apparatus available locally or easily constructed. It's locally organized. It's regional, so every ALOP includes participants from neighboring countries. It's taught by a team of teacher trainers, from developing and developed nations who volunteer their time. So presenters from the Philippines, Tunisia, Australia, United States, Canada, and others. And it often involves training of local trainers who can present future ALOPs. Here's a photo of the original members of the ALOP International Facilitator team. And a member of the team as well. So I'm not in, I took this photo, I believe. And here's one trainer who was trained as an assistant facilitator at one of our ALOPs. And he, in fact, Widi, was trained at an ALOP we just recently held in Bandung, Indonesia, last October. And here he is presenting a couple of demonstrations as part of that ALOP training. Inexpensive equipment. So, for example, instead of using an acrylic lens like the one I just showed you before, you can make a perfectly nice cylindrical lens by taking a plastic food container like this and filling it with water. And 2 inexpensive light bulbs connected to a 9-volt battery. And here's what you get. There's the lens that's filled with water. The 2 light bulbs are on, and if I turn out the lights, that I get exactly the same pattern as I saw with the much more expensive acrylic lens. Inexpensive lasers, cellophane filters, gratings from old discarded discs and DVDs, flashlights as light sources, paper towel rolls for spectroscopes, slits scratched into mirror surfaces or painted pieces of glass. So the cost of a kit for an ALOP is very, very inexpensive. An ALOP is a week long, 5 days, and there are 5 modules as part of an ALOP. Introduction to Geometrical Optics, Lenses and Optics of the Eye, Interference and Diffraction, Atmospheric Optics, and Optical Data Transmission and Wavelength Division Multiplexing. And all of these are contained in the Active Learning in Optics and Photonics Training Manual. It includes an introduction to active learning, the 5 modules with student materials and teacher's guides, and it also includes the Light and Optics Conceptual Evaluation and an action research guide to tell you how to do research in education research in your classes. There's been a second generation of ALOPs in French, Spanish, and Arabic. And in fact, the book has been translated into those languages. And here are the French, Spanish, and Arabic covers for the training manual. It's also been translated into several other languages. Let me just say a little bit about my module, which is the one on geometrical optics, the first module. And it is a combination of three things. Some activities from real-time physics, module 4, but not the ones that use technology. There are many activities in that module that use very, very simple apparatus. Interactive lecture demonstrations, as you've seen. And also the final element is optics magic tricks, adapted for active learning. And let me show you what I mean with an example of an optics magic trick. And one of the optics magic tricks I do as part of the training is one called the reappearing test tube. So here is a glass test tube, a hammer, and my magic wand. And what I do is I shatter the glass test tube in an envelope, shatter into many, many pieces, and I put those pieces in a magic fluid. This is the magic fluid. I say the magic word, which is ALOP. And there I am with my magic wand and the magic word ALOP. And then I pull a whole test tube out again. The test tube, the pieces of the test tube have become whole again. And I then show the students or the teachers that in fact, if I put the same test tube in water, I can see it perfectly well. And if I hold the same test tube in air, I can see it perfectly. And then I ask them in small groups to discuss the following questions. How did I make the test tube reappear? Why can you see the test tube in water or air, but not in the magic fluid? What is special about the magic fluid? What property of transparent media determines whether reflection takes place at the boundary between them? And of course, the idea here is for students to conclude the magic fluid has the same optical properties or the same index of refraction as the glass of the test tube. And by the way, just in case you're wondering, the magic fluid is cooking oil, corn oil. The glass of the test tube is Pyrex glass. And those two things have almost exactly the same index of refraction. So it's fun to do such tricks, but it also engages the students, and it wouldn't be active learning without having a set of learning questions like this. Let me just describe one other thing from ALOP, and that is the Capstone, which is Module 5, which is on optical communication and wavelength division multiplexing. And so it examines analog versus digital transmission. So for example, having students play with 2 cups and a string as an analog transmission system, and moving on to look at a digital transmission system, which involves an LED and an optical fiber. And this involves many concepts that we've taught in the other modules of ALOP: rays, total internal reflection, dispersion, absorption, and scattering. And then finally, wavelength division multiplexing, where students see that you can put multiple signals down the same fiber at the same time and divide them into their components, their different colors, by using a prism or diffraction grating for dispersion, which are things that, again, were studied in a previous module. This, by the way, is based on an article that appeared in the American Journal of Physics, written by Alex Mazzolini and a colleague of his. There's Alex again. Here's what the apparatus looks like. A few students work with it. And now I just have a few photos to show you. These are photos taken in December in Pune. And so there I am with the group. And here's the poster for that workshop, Active Learning in Optics and Photonics. Some students working on Module 2, you can see the lens. And the optical bench consists of a meter stick and a piece of clay. Some students working on Module 4, looking at scattering in a liquid with a suspension in it. And again, the same thing. The liquid represents the sky, light being scattered by the sky. And you can see the light that's scattered out the sides has a little bit of a bluish tint to it, like the reason why the sky is blue. There's the whole group. Again, you can see Suad sitting there and me. And by the way, I'll just mention that when we were in Pune, we also did a presentation. I did a presentation of some optics magic tricks to some girls at the Laila Poonawalla Foundation in Pune. So here is me doing the demonstrations, and here is the whole group. Suad, me, Alex, and so on, and all the girls. It was already mentioned that we won the SPIE Educator Award in 2011. That is the presenters of ALOP won that award. It wasn't an individual award. Okay, we come to the last topic of my talk, which I threw in at the end, and that is over the last 6 months, as I worried about how people would be doing active learning when they weren't meeting with students and students weren't meeting with each other, I had the idea to put some interactive lecture demonstrations online. So at least students could work on them at home and at least have the opportunity of making predictions before they made their observations. So this is an at-home active learning strategy. And here are the design features. So they're based on the interactive lecture demonstrations that are in the ILD book I've already talked about. They're designed to introduce concepts or clarify them. The assumption is that there will be other at-home things that students are doing besides these. They envision students working alone. So I decided not to incorporate any requirement of group work or collaboration, even though in these nice software packages like Teams and Zoom, it's possible to have chat rooms. There are many people who may not want to do that or who may not know how to do that. And therefore, I set up a learning environment where students, which could be used without doing that. Of course, you could incorporate chat rooms if you wanted to, but they can be used without chat rooms. They do incorporate predictions, observations, and comparisons and explanations. So they don't include any group discussions, but they do include the other elements. And instead of having live demonstrations, they make use of videos, photos, graphs, simulations, and for the experimental observations. So I want to show you an example. This link should be in the chat, so I'm not going to dwell on it and have you copy it down. You should be able to find it in the chat. I'm going to click on it, and you see it takes me, which first of all describes what these are, and then at the bottom of the page are a list of 26 different sets of interactive lecture demonstrations. And you can see they're on topics in mechanics, electricity and magnetism, light and optics, sound, simple harmonic motion, and finally heat and temperature. of them. And the one I'm going to show you is the one on polarized light. So I'll click on it. And this is what you would see if you clicked on it. You would see the prediction sheet. And if I click at the top, the print is rather small, so I don't know if you can read it, and I don't suggest you try to read it. But as you see, it says click here to download the prediction sheet. So I'll click here, and you'll notice that that sheet is being downloaded. And if I open it, there it is. There's the prediction sheet, and it's in Microsoft Word. And so students can type their predictions on this sheet, and if you they can send it to you. So I'm going to get rid of that for now because I'm not going to use it. I'm going to just show you a couple of the demonstrations and how they work. So here's a demonstration where we have unpolarized light. Students are told they have unpolarized light. It comes and it strikes a piece of polarizing filter that has its axis pointing upward. And then I'm going to analyze the light that comes through with another piece of Polaroid. So you're asked to make a prediction. What will be the direction of polarization? And what will happen to the intensity? Okay, so students can make a prediction, and then it says only after you have made your prediction, click here. Actually, I'm just going to show you one of them. Click here to download and view video of the experiment. So I click here. You see the video is downloading. Takes just a few seconds to download. And now I'm going to open the video. And there it is. And you see there's a flash. There's a piece of Polaroid right there in front of the flash. I'm sorry, there's no Polaroid. I'm rotating a piece of Polaroid in front of the flashlight. And you see that there's no change in the intensity no matter how I rotate the Polaroid. So that's the observation. And then you're asked some questions. And now I'm going to go on to the next one and just show you one more because I think I'm running a little bit out of time. And this one says, suppose that I put a piece of vertical Polaroid here, and then I put a second Polaroid and rotate it so that it's at 90 degrees to the first one. Predict what will happen. So again, I make a prediction, and then only after I've made the prediction, I can look at the video. So I'll download that video. And open up, and here we go. And so there's the demonstration, and we see quite a different thing. So that's an idea of what these things look like. By the way, I use lenses from a pair of sunglasses because I was isolated. I couldn't get to my laboratory. So I had to use equipment that I had sitting here. And that's why I took the lenses out of a pair of Polaroid sunglasses to do it. Okay, I'm going to close this. I'm gonna just show you. Actually, I'm not, because I don't want to use up more time. I'll close this, and I'm going to move on. I'm almost done.
Sir, you can take time.
Okay, actually, if I can take just, oops, my cursor has now quit on me, so I actually can't do what I wanted to do anyway. So I'm gonna. Actually, that's going to be a problem, maybe. Here's the list of interactive lecture demonstrations again. I think I will finish, but I will open to any questions that you have. So, but the main message is you must engage your students in the learning process. If you don't engage them in the learning process, the evidence from physics education research is that they will not learn. They will not learn physics concepts. So actually, let me just try to see if I end the show, do I get my cursor back? Yes, I do. Okay, actually, how much more time do we have in this session?
Sir, you can take as per your convenience.
Let me take questions, and then
Yes.
if there's any time at the end, I'll show you another one of these online
Yes.
interactive lecture demonstrations. So I'll close this down for now, and bring the window back up. Yes, are there any questions?
Dear participants, if you have any questions, please raise your hands so that we will unmute you and allow you to ask the questions.
I hope I didn't go too fast.
No, no, sir, no, sir. It's
Comments. Let me ask a question.
yes. Sir.
Does anybody have a thought about whether these would be useful, whether these strategies would be useful to you?
Yes, sir. They are useful for us at least.
I have a question.
Yes.
Yes, sir.
Yeah, I have got a question, sir.
Yes, go ahead, please.
So, can we have such ILDs for higher courses such as quantum mechanics or something?
Okay, there are, I'm not aware there are ILDs for more advanced classes, but there definitely are some new strategies for teaching more advanced classes. And what I suggest to you to find some of these, the best place to go is to something called Phizport, which is a website associated with the American Association of Physics Teachers. And I believe, actually, I'm going to, while you're asking the question, I'm just going to make sure of the link. Hang on just
Would
one
you
second.
please share the link, sir?
Yes, I want to make sure that oh, good, it's easy. So the link is Phizport, which is PHYSPORT.org, O-R-G. Is that clear?
Okay, thank you, sir. Thank you.
Is also to go to AAPT.org. And there are many resources there. And one that I particularly direct you to is something called Compadre. But you will see that at Compadre.
Yeah.
Yes. Okay.
Oh, yeah. Compadre. Yeah. Thank you, sir. Thank you.
You're welcome. You're very welcome.
Dear participants, if you have questions, you can unmute yourself and ask the questions to David.
Somebody has
David?
Yes,
David,
Suat.
can I add something, please?
Of course.
Regarding quantum physics.
Yes.
The last question.
Yes,
I introduced my quantum physics course using the spectroscope you showed in your presentation. Just using, for example, sodium light source or cadmium light source, and using spectroscope, I can show that the spectrum is not continuous.
Very
Okay.
good.
Yeah,
Yes.
and or hydrogen light source, and compare the spectrum to the sunlight, for example, sunlight, and show that in that case the spectrum is continuous for the sun, and for the hydrogen the spectrum is not continuous, and then go back to the quantification of the energy of the
Yes.
atom and so on. So it
Yes.
might be a very, very good introduction to quantum mechanics.
Yes.
Thanks to
Yeah,
this.
you actually you raise a very nice idea, Suad, and
Yeah.
that is you should all be aware,
Yeah.
and I think many of you are aware, that although your students may have reached advanced classes, they have not necessarily had many experiences with these phenomena. So they may never have seen a discontinuous spectrum Suad is describing. So seeing this can be a dramatic motivation for them to then learn about quantum mechanics and about discrete states and eigenstates and so on, which will make them more interested because they have a motivation for learning it. And I will also say that research has shown that even students in advanced courses and even students in graduate courses, if they have been taught their undergraduate physics in a completely traditional way, they have many, many misconceptions about physics concepts, just like introductory students do. Some of the same ones.
Yeah, that's true. Yeah,
Okay.
thank you. And that's true, sir.
Yes.
Thank you.
Okay, you're welcome. Other comments, questions?
Dr. Shivalkar, sir, please unmute yourself and ask the question.
Yeah.
Sir, hello, sir.
Yes, sir.
Yes, sir.
Can I audible?
Yes,
I
yes.
hear you.
Hello?
Yes. Yes, I hear you.
Okay, sir. Yes, sir. You are giving brief knowledge about actual learning model,
Yes.
and which it is very much helpful to us for actual teaching time. So I
Thank
have
you.
a small question. I have a
Yes.
very small question about this actual learning model.
Yes.
Can we use this active learning model for practicals, undergraduate physics practicals?
Undergraduate physics practicals.
Yes.
Okay. Now, when you say practicals, I don't know if you're talking about exams or hands-on work. What do you mean by practicals?
Hands-on work, sir.
Practicals,
Hands-on.
yeah, like spectrometers. If we use, as you shown that spectral glass,
Yeah.
and you show the polarization, like that. We have to use some models for doing the practicals for a group of students, or
Yes.
the more. Supposed to be we have the more than 100 students, and we demonstrate a practical for more than 100 students.
Okay. So
What
practical means
laboratory
actually
laboratory work,
laboratory, but you do
Yes,
it with 100 students
yes, laboratory work.
at one time. That's what interactive lecture demonstrations are designed for. That's what I do. I do interactive. Look, I'm retired, so I'm not teaching now, but when I taught general physics at the University of Oregon, every week, once a week, I used a whole lecture to do interactive lecture demonstrations, and my lecture had 200 students in it. That's the purpose, because I only have one set of equipment. And I know surely in India, in many classrooms and many schools, a big problem you have is you don't have equipment, or you don't. So this is why we developed ALOP, and this is why ALOP uses very inexpensive equipment, because we recognize that optics. You want students to have practical experiences, but you don't have any equipment or you don't have much equipment. So everything is very inexpensive. By the way, yes.
Okay, I have one more question.
Yes.
By using these models, can students get knowledge about that experiment?
Interactive lecture demonstrations are designed just like, look, a lab experiment that a student does is designed, well, in my mind, a lab experiment should be designed for students to learn some limited area of physics. In traditional laboratories, often all that students do in a laboratory is they measure some number, like they measure G, they measure the gravitational acceleration. To me, that's not a very useful laboratory. But in my mind, a laboratory, they should learn some set of physics, some set of concepts. And that's what a set of interactive lecture demonstrations tries to do, to teach students a set of related physics concepts. And believe me, it does it much better than lecturing to them. So I wouldn't say that a course should be completely taught that way, but it's a way of getting students to understand concepts better. That's the idea.
Okay, thank you, sir.
Okay.
Thank you.
Other questions?
Naya madam, please ask your question. Neha ma'am, unmute yourself and ask your question.
Hello.
Hello.
Yes.
Good morning to all of you, sir. David,
Good
sir,
morning.
I really liked your session and I really like this concept of ILD in physics.
Yes.
Sir, my question is that is it possible to teach all topics of physics through ILD, because there is a lot of syllabus in physics in our classroom. My personal question from you is that do you teach all topics of physics with ILDs on or are there some other methods you in your classrooms?
Yes, okay, good. It's a good question. So there are many strategies that have been developed to improve the learning of physics. And really, in this day and age, to develop a course in physics that's an effective one, in my mind, if I were starting out right now, if I were teaching right now, I would combine a whole bunch of different strategies. And it would depend on the students I'm dealing with, how many students do I have, what equipment do I have, what environment do I have. There are things like peer instruction. There are group learning strategies that you can use in classes. There are ILDs, there are real-time physics laboratories. And it really, there are many, many different strategies. I would say really interactive lecture demonstrations are a way of complementing others because they are very effective at teaching a limited number of concepts. We have developed them in many, many different areas of physics, but they don't make up the entire course of physics. They are a material that you can use in your class as part of your class. So again, I would say if you want to see what's available, the best thing is to go to Phizport. Did you put those links on the chat as well?
Yes.
Yeah. So on the chat, you can find a link to Phizport and to AAPT, and those are places where you can find the types of things that are available, and that's what I would do.
Okay, okay. Thanks a lot, sir.
Okay, you're welcome. Other questions? The reason why I'm not looking at the camera is because I'm trying to find another link to give to you. Because there's actually a link to the ALOP manual. And if I can find that, I will give it to you. Wait, actually, so are there other questions? Because I can probably. Yeah, go. Any other questions, comments? Okay, actually, I think I can find this. Oops. Okay. No, but if you want to if you want to be done, I can just I'll send you the link because I can't find it right now. But there's a link to to apply for an ALOP, for example, or to download the manual, the ALOP manual. So I can give you those. By the way, if this pandemic finally is over and we do another ALOP in India, I think we have promised to do one for the next one for the Leela Poonawalla Foundation. So,
Yes, sir.
so the next one would have to be after that. Let's hope.
Sure, sir.
Yes. Okay. Anything else?
David, can I ask a question?
Of course.
Regarding the ILDs you showed us in the end of your presentation.
Yes.
Could everyone access them, or are they only for your institution?
Oh no, I gave you the link. They are.
Sorry.
You go to that link and they are all there.
Okay.
They happen to be on the server from my university, and good. I keep imagining that at some point someone at my university is going to say you can't do that, but so far that hasn't happened.
Okay, so maybe you can put the link on the chat also.
It is.
I
think it is on the chat already.
Yes.
Thank you.
Yeah.
Okay, thank you.
And please, by all means, any of the 102 of you, feel free to use those. If you do use them, I would love to hear any feedback about them, because look, frankly, 6 months ago in March, maybe that's 7 months now, it's hard to keep track. I thought, look, people have to teach online. They are going to completely give up on active learning, because what are you going to do? You're going to stand in front of a camera and broadcast yourself over Zoom or Teams, because that's the easiest thing to do. And I don't blame people, because quite frankly, I say it very frankly, I am very glad that I am not teaching now, because it would be very difficult, and it is very difficult, to teach in an effective way when you have to do it online, and suddenly you have to do it online.
Yes.
That's why I decided, and it took me 6 months to get them all online, but pretty much every interactive lecture demonstration sequence that's in that book is available to anybody online. So there they are. feel free to use them. If you find something wrong with them, let me know and I'll fix it. If you like them, let me know. If you don't like them, let me know. I have had 3,100 hits to that web page, but I have gotten 5 emails of people telling me something.
Okay.
So,
Thank you.
okay.
Okay, thank you.
All right. Well, I'm done. If there's no more questions, is that okay?
Yes, sir. Yes, sir.
Yes,
I
sir.
mean, it's been a pleasure. I wish I could see you. I've seen a few of you who have your cameras on. It reminds me of being in India. I love visiting India except for the air pollution, but otherwise it's very, very, very fascinating, interesting place. And I've been fortunate to be in 3 different areas in India, and I look forward to coming back again sometime. But this is the second best, and it makes me feel very warm and fulfilled to have had this opportunity. So I thank you very much. And if I can help in any other way, then please let me know.
Yes. Thank you, sir,
Thank you,
for
sir.
spending your
Thank you,
special
sir.
time with us from your
Thank-
busy schedule, and
Yes.
very thought-provoking guidance on
Yes.
real-time physics, active learning labs, interactive lecture demonstrations, home adopted active learning, the enlightened optics concepts evaluation, a very good questionnaire and sheet developed by the ALOP members. We are happy to learn the various characteristics of the curricula that make the curricula very effective, and definitely our participants and we will try to adopt this active learning in your curricula so that the curricula will be active and effective, and our students will learn a lot of things from this curricula. Thank you once again, sir.
Okay.
Now I
Okay.
request